Hello, welcome back. Mr. Munyon here with activity 31-3. We're going to be focusing on finding the area of regular polygons. In activity 31-3, we have a couple of goals to find the area of regular polygons and then solve those problems. So develop a formula and then solve problems with that formula. All right, so how do we find the area of regular polygons? First, we know that a regular polygon recall that a regular polygon is equilateral and equiangular. So all of the sides are equal and all of the angles are equal. An apothem of a regular polygon is a perpendicular segment from a midpoint of a side, so from point S, to the center of what would be an inscribed circle around that shape. So if I draw this point here, that would be the center of a circle inscribed around that shape, as you can see in the diagram. So it says, consider the tabletop template of a regular hexagon as shown. Draw all of the radii from the center. So if I was to connect to the vertice that's touching the circle, that is considered a radius of the hexagon. And you can draw all of these on there. And we get a bunch of triangles that are created, which is kind of beginning of how we're going to figure out the area of these regular polygons. So what is the measure of each of the central angles formed by the radii? How do we figure that out? So the central angles formed here, how do I figure out what that is? Well, I know there's a total of 360 degrees around any point, and if I created 1, 2, 3, 4, 5, 6 total triangles there, because there were 6 sides of the hexagon and all of those are the base of one of the triangles, that means 360 divided by 6 is 60 degrees. So each one of those central angles is going to be 60 degrees. It says classify the triangles formed by the radii and their side links. Okay, so classifying these by side links, I know that if I draw a radius of a circle here and here, every radius on the circle is the same. So these two have to be congruent to each other. So based on just those two pieces, I know for sure that it's an isosceles triangle. All right, in this specific case on a hexagon, we know that these base angles also have to be congruent, and since each triangle has to add up to 180 degrees, there's only 120 left. Divide these by two congruent angles, we actually get 60, 60. So this is actually an equilateral triangle as well on this hexagon. Other ones, though, if we had like a pentagon, an octagon, any other shape, it would just create an isosceles triangle there. Find the area of a regular hexagon with a side length of 4. Show our calculations. Regular hexagon. So area equals, let's look at one of the triangles. So 6 times the area of one of those triangles, or area equals 6 times 1/2 base times height. So if the side of this is 4, I already know the base is going to be 4. Oops. All I need to do is figure out the perpendicular height, or that other piece that we were just talking about called the apothem, that goes from the center of the hexagon to the perpendicular center of one of the sides. So how do I figure that out? Conveniently, I do create a 30, 60, 90 triangle right there when I cut that in half. And cutting this in half, since it is the center, will be 2. So that means this side would be 2 square root 3 and 4, based on what we know about special right triangles. So the height of that triangle would be 2 root 3. So 2 square root 3. And we could plug all of this in. 6 times the area of the triangle, 1/2 base times height, we could get the total area of this hexagon. Now there's seems like a decent amount of work. It actually wasn't too bad, but it's a decent amount of work. We're actually going to summarize this and make it a little bit easier. So notice right here, it says refer to the diagrams of these regular polygons. How many triangles could you form if you drew all the radii? Well, if it has 5 sides like this pentagon, you're going to be able to draw one triangle for each side and make that the base. So this should end up having 5 triangles. And sure enough, we do have 5 triangles right there. This one is an octagon. It has 8 sides. So 1, 2, 3, 4, 5, 6, 7, 8. There should be 8 triangles on there whenever we draw this. And sure enough, there are 8. I didn't do it perfectly, but we do get 8 on there. So 5 and 8. All right. For the next question, it says, what is the measure of each of the central angles? So how can we figure out the central angles? Just like we did on the hexagon, we can take 360 degrees around that center point and divide it by however many isosceles triangles we created. So this one, 360 divided by 5, tells us each of these central angles is 72 degrees. 360 divided by 8 gives us 45 degrees for each one of these. Okay, so then for each one of these we get it says classify the triangles formed by the radii and their sides. We get 2 isosceles triangles because the radii are going to be congruent to each other. The angles aren't 60, so it's not going to be an equilateral one. All right, to save a little bit of time on deducing the formula, I want to point out that all we're doing is using triangles. So let's pretend for a second, if I want to find the area of 5 triangles, I can save a little bit of time right here because I know h, the height of these triangles, is just going to be the apothem. So that piece right there is the apothem of the shape. So that could be replaced with an a. So area will equal 1/2. And then h is being replaced with the apothem. And when I multiply the base times 5, the base multiplied by 5, 1, 2, 3, 4, 5, the base of one triangle, if you multiply by 5, ends up just being the perimeter. So I could replace multiplying the base times 5 with perimeter of this shape, and I could switch the order of these because multiplication is commutative. I could write this as 1/2 apothem times perimeter. Some people pronounce it apothem, some people pronounce it apothem. I'm going to call it apothem for each one of these. So here is the formula for area of any regular polygon, which ultimately is what we're trying to get to. And notice if the number of sides changes, it doesn't affect this formula because that would mean this number here would change and it would still end up being the perimeter when you multiply the base by the number of sides. So like on this octagon over here, it's still going to be 1/2 apothem times perimeter because the perimeter still comes from one of the sides times however many sides there are. And the apothem is still like the height of that triangle. So ultimately for the question down at the bottom, we do get area equals 1/2 apothem times capital P representing perimeter. All right, so now let's practice using this. Here we have an example that walks us through how to find the area of a regular polygon given one of the sides. In some cases, we can use special right triangles. In other cases, we might have to use trigonometry if it's doesn't happen to be a 30, 60, 90 or a 45, 45, 90. So first step, what I would do is start by writing down the formula and see what you can plug in. Typically, you're going to be able to figure out the perimeter really easily and plug it in, and you're going to have to do a few steps to figure out the apothem. So on this octagon right here with side lengths of 8, perimeter is real easy. Just 8 times 8 sides gives you 64. And now you're going to have to do a little bit of work to figure out the apothem. So first step is create, if you want to draw all of your isosceles triangles or just one of them, you can. Pick a side that you're going to use and create an isosceles right triangle. And notice that when you draw the apothem, it cuts that side in half. So you could label a right triangle with one of your legs as 4. From there, you would need to figure out what the central angle is and then cut it in 2 to figure out one of your angles on a right triangle. And that's what they did right here. They figured out the central angle is 45, cut it in half to figure out one of the angles on a right triangle. So they eventually end up with a right triangle where they know one of the angles is 22.5. They know one of the sides is 4 inches. And they're solving for this piece right here, which conveniently is called the apothem, but also happens to be the adjacent leg to the angle that we know, which means we could use trigonometry to find this. We could use tangent using the opposite and adjacent legs to solve for this. So they use the tangent function using the 22.5 degree angle. The opposite side was 4. They plug that in and solve. We get that A has to be approximately 9.7. Then you can plug that into the formula to find the area. So a little quick, but let's do that piece by piece. Let's practice this. Calculate the area of a regular pentagon with a side length of 12. I'm going to take this to a different page where we have a little bit more room. I'm going to start by writing down the formula for area of a regular polygon, and then I'll plug in my piece. Equals 1/2 apothem times perimeter. If this is a regular pentagon with 5 sides and one of the sides is 12, you could do 12 times 5. So perimeter equals 12 times 5. So perimeter equals 60 meters. So I can go ahead and plug that in. Area equals 1/2 apothem times 60. So all I need to do now is figure out the apothem. So the way we can do this is draw our radii from the center of the pentagon to a couple of vertices and create an isosceles triangle. And I'm going to go ahead and draw the apothem in there so that I can figure out one of the sides of my right triangle. So if the entire side is 12, that means half of that would be 6. So I have a right triangle. For sure that I know that one of the legs is 6. I'm going to redraw that one a little bit bigger so we have this. I also need to figure out this angle right here. And I can do that by taking the central angle here. There's 5 triangles, so 360 divided by 5 tells me that entire angle is 72 degrees. And because when I draw the apothem, that cuts that in half right down the middle, that means each one of those is going to be 36 degrees. All right, so I know this angle is 36 degrees. A little shortcut you can do is actually take 360 and divide it by twice the number of sides, because you're actually, although you create 5 isosceles triangles, you're actually creating 10 of these right triangles. For each isosceles triangle you create, that's taking up a whole side, you do create 2 right triangles. So there's 1, 2, the next one would be 3, 4, 5, 6, 7, 8, 9, 10. So 360 divided by 10 gives you 36. So now that I have this, I want to solve for the apothem so that I can eventually plug it into our formula up there. So I know that this is the angle of 36 is opposite of 6, and adjacent leg is what we're solving for. I can use the tangent ratio. Tangent of an angle is going to be opposite over adjacent. Tangent of 36 degrees equals opposite is 6. Adjacent is A. If you wanted to solve for A, you can multiply both sides by A, divide both sides by tangent of 36. Your first step is multiply both sides by A. And then your next step is divide both sides by tangent of 36. So once again, they do just end up A and tangent of 36, just switch places, and that'll happen whenever your variable's in the denominator of any of these trig functions. You'll be able to do that. So let's plug in our calculator and check to see what we get. 6 divided by tangent of 36, and we get approximately 8.26 for that side length. Oops, go back to this one. All right, so 8.26, let's go ahead and plug that one in. So area equals 1/2 8.26 times 60. And now we can plug that in our calculator. 1/2 times 8.26 times 60 equals 247.8 on that one. So we get the area 247.8 8, and area, this should be in square units, so meters squared. Okay, let's go back and try another one. So we just got 247.8 meters squared. Let's try the next one, a hexagon with 18 centimeter sides. Let's see what we can do for this one. So first step is write down the formula again. And once again, the perimeter we should be able to get pretty quickly. And I'm going to go ahead and plug that in. Equals 1/2 A. So 18 times 6 would be 108. Okay, and now we need to figure out the apothem, and we can do it the same way that we did before, drawing our radii to create an isosceles triangle, drawing the apothem to create a right triangle using the central angle. So we're going to go through the exact same steps. We're just practicing it again to make sure we know what we're doing here. So go ahead and find your isosceles triangle. If you want to draw the apothem now, you can, and label that the side, one leg of your right triangle down here at the bottom. If the whole thing is 18, half of it should be 9. All right, so one leg of my right triangle is 9. For your central angle here, we can take 360 degrees and divide by the 6 triangles that we could create on a hexagon, and we get that this whole angle here is 60 degrees. If I was to cut that in half, this angle would be 30 degrees. So now that I have that, I have enough information on a right triangle to solve for the apothem of this shape. I know that there is an angle up here that was half of 60, it was 30 degrees. I know this side down here is 9, so I should be able to solve this using trigonometry again. So same tangent function, tangent of an angle equals opposite over adjacent. Tangent of 30 degrees equals opposite over adjacent. All right, and then to solve for A, we can switch it with the other side of the equation. And now we can plug this in our calculator to figure out the apothem. So 9 divided by tangent of 30. 9 divided by tangent of 30, and we get about 15.59 as our answer for that one. So approximately 15.59. So now let's go ahead and plug that in. All right, and we can plug that in our calculator. Area is going to equal 1/2 of 15.59 times 108. So we'll type that in our calculator. Times 108. And we get 841.86 as our answer. So 841.86. And the units will be square units, so centimeters squared. So 841.86. All right, so now that we've done this a couple of times, we should be able to do this for basically any shape, because any regular polygon, because it's going to be the exact same process. Write down the formula. You can get your perimeter real easy if you know one of the sides. Draw your isosceles triangle, use the angles in the side that you know to solve for the apothem, and then plug in the apothem into your equation. The only other type of problem you might see is maybe you're given a radius, and you could still use Pythagorean theorem, or not Pythagorean theorem, you could still use trigonometry to solve for the apothem, or you might have a problem on a coordinate plane where you could use a different method, which is why this is the only other question we have on here. So it says find the perimeter and area of regular polygon ABCD with these vertices. Well, if it has 4 vertices, it has 4 sides. What do you call a regular polygon with 4 sides? That would be a square to be a regular polygon with 4 sides. So we don't need to use the formula This is a much easier question. How do you find area of a square? Just the side times the side, base times height. For a rectangle, you get the area. So if the sides are the same, it's just base times height, side, or side squared will get you your answer. So all I need to do is know the length of one side, multiply it by 4 to get the perimeter, or square it to get the area. So let's go ahead and pick any two consecutive points, find the distance, and then we'll get the perimeter and area. So the distance formula is just the square root of changing x squared plus changing y squared. If I look at the x values and ask how much do they change, from 7 to 9, it changes by 2. So changing x goes by 2 units. And the y values from 8 to -1 goes down by 9. All right, so 2 squared is 4, 9 squared is 81, square root of 85, so the distance is going to equal square root of 85. So then multiply it by 4 to get the perimeter. So the perimeter is just 4 times square root of 85. You could plug that in your calculator if you wanted to, but that's the exact answer. If you get a decimal, you could round it for the approximate answer. But then area, all you have to do is square it. So whatever that side length is squared, in this case the square and the square root cancel out and you just get 85. The units, whatever they are, they'll be units squared. All right, so that problem was actually a lot easier than maybe we thought it was, because it ended up being a square instead of a different polygon like a pentagon, hexagon, heptagon, octagon. All right, so at this point, I think you guys are ready to try some. Go down to questions 3 through 6, and especially like question number 5. That's where you actually need to find the area. See if you can answer these. Pause the video here, and when you restart it, I'll have the answers for you. All right, now that you have taken a moment to try questions 3 through 6, let's look at the answers and see what we get here. 3 says the properties of what type of triangle can be used to determine the apothem of a regular hexagon. We end up using an isosceles triangle and a right triangle. We need to use both of those. We need to create an isosceles triangle first. And then we turn that into our right triangle to help us figure out. Obviously not drawn to scale here, but we use both an isosceles triangle and right. Okay, it says write a formula that can be used to determine the perimeter of an n-gon, so any size shape. All you need to know is any of the sides, whatever the side length is, s, and then multiply it by the number of sides. And we did that before, will equal the perimeter. So whatever side you're given, just take that and multiply it by how many sides you have, and you'll figure out the perimeter. All right, question 5 says find the area of a regular octagon with 7-inch side. With a side of 7, we always start by, if we want to find area, start by writing down the formula for area of a regular polygon. The perimeter should be pretty easy. Just multiply 7 times octagon has 8 sides, so 7 times 8 gives us 56 on this one. So area equals 1/2 apothem times 56 is the first thing we can plug in. All right, and then from here we need to solve for the apothem, same way we've done before. Create our isosceles triangle, drawing the radii, turn it into a right triangle, use the central angle and however many triangles there are, or use however many triangles are to find the central angle, create a right triangle where we know one of the sides and one of the acute angles to help us figure out the apothem. So that's what we're doing here. The side lengths are 7. Cut that in half. We get each side of this right triangle right here will be 3.5. I also need to know this angle up here. So if there are 8 of these isosceles triangles, 360 divided by 8 tells me each one of these central angles would be 45 degrees. And then if I cut that in half for the right triangles, each one of those angles is going to be 22.5 degrees. So that means if I was to draw just that right triangle a little bit bigger so I can see the pieces, I get this angle here is 22.5 degrees. This side is 3.5, and I'm solving for the apothem here. Okay, I can use trigonometry to do this. Once again, I'll be using the opposite side and the adjacent side from that 22-degree angle. So once again, it's going to be tangent. So tangent of an angle equals opposite over adjacent. Tangent of 22.5 degrees equals opposite 3.5 over adjacent, the apothem that we're solving for. To solve for A, we can switch it with the other side of the equation, and we end up getting the apothem equals 3.5 over tangent of 22.5 degrees. So we can type that in our calculator and see what we get. 3.5 over tangent of 22.5. And it looks like we get about 8.45 as our answer on this one. So about 8.45 inches on there. And I can now plug that up here. I get the apothem is 8.45. So let's go ahead and do that and then type that in our calculator. All right, so 1/2 8.45 times 56. And looks like we get 236.6 as our answer. So approximately 236.6. So 236.6 inches squared should be the units for area. So 236.6. All right. Last one, Seth states that the radius of a regular polygon is never less than the apothem. Do you agree or disagree? If so, provide justification. If not, provide a counterexample. So it says the radius is never less than the apothem. Where is the radius? On this one, the radius would be this blue line I've drawn right here to a vertex. Is the radius never less than the apothem with this dotted blue line right here? Well, if I look at the right triangle there, I notice the solid blue radius is the hypotenuse of a right triangle, and the apothem is one of the legs. Could the hypotenuse ever be less than a leg on a right triangle? No, the hypotenuse is always the longest side of a right triangle. So the radius will never be less than the apothem on a regular polygon. So do you agree? Yes. And that's because the hypotenuse on that right triangle has to be the longest side of that right triangle. All right, some more practice with the lesson practice at the end here, 7 through 10. Let's go ahead and specifically 7, 8, and 9. Well, all of these are good ones because you just find the area. I'm going to put the answers up here for you. I'm not going to go over but just one of these for you. I'll go over number 10, and I'll have the answers for the rest of them. Okay, so here are the answers for 7 through 9. For some of them, we needed the perimeter and area, and some we just needed the area. Let's look at number 10 now. I mentioned I was going to go ahead and go over that one. So find the area of a regular pentagon with a radius of 8. This one is the radius, not the side length, which is why I did want to go over this one. So let's say we have a regular pentagon. Doesn't have to be perfect. With a radius of 8. Not a side length of 8, a radius. We need to figure out the perimeter on this one, which means you need to figure out both the apothem for this formula and this piece down here. You could call this x to be able to figure out this problem. So if I started down by writing down the formula, area equals 1/2 AP. We can't just figure out the perimeter real quick on this one and plug it in. We have to do trigonometry to solve for both the apothem and the perimeter. So first step is figure out the central angle and then cut that in half to figure out this angle here so that we can use a right triangle trigonometry to solve for these. So 360 divided by 5 means each one of those angles on the isosceles triangles is 72. So this whole angle here is 72 degrees. And then cut it in half, we do get each one of those would be 36 degrees. So I do have a right triangle with a hypotenuse, a radius on that pentagon is 8. And then I need to solve for A and X on this one with a central angle of 72. It gives me each one of these 36 degrees. So on this one, we're not going to use tangent because we don't know the opposite or the adjacent. So I'm going to start by using either sine or cosine to help me figure out X or A. So let's start with the cosine function. We can figure out A. So cosine of an angle equals adjacent over hypotenuse, or cosine of 36 should equal the adjacent A, this is what I'm solving for, and the hypotenuse is 8. So multiply both sides by 8, and you get 8 times cosine of 36. Plug that in our calculator, and we get about 6.47 for our answer on that one. So A equals about 6.47. We can do the same thing for to solve for X, and that will help us. Once I know X, I can just multiply it by 2 to get the whole side length, and then multiply it by 5 to get the perimeter. Or 2 times 5 is 10. I can just figure out X and then multiply it by 10 to get the perimeter as well. So this one would be opposite is X and hypotenuse. So I'd be using the sine function. So sine of an angle equals opposite over hypotenuse, or sine of 36 degrees equals opposite is X, hypotenuse is 8. Multiply both sides by 8. You get X equals 8 sine of 36, or X approximately equals 8 times sine of 36. Let's see what we get. And we get 4.7 approximately for that one, 4.7022. Okay, so then to find the perimeter, we would need to take X and multiply it by 2 to get the whole side, and then once we know the side, we would need to multiply it by 5, or perimeter will equal X times 10. So 4.7022 times 10 gives me 47.022. Now that I know the perimeter and the apothem, I can go ahead and plug those in up there. So area equals 1/2. For the apothem, I got 6.47. And for the perimeter, I got 47.022. So type that in our calculator, 6.47, 47.022. Looks like we get the area equals approximately 152.12. And the units on this would be centimeters squared. And so this part is what made it different from the rest of the ones that we've done. If you got that before I did, great job. All right, we're done with activity 31-3, all of activity 33. I would definitely recommend you practice a few more of these just to make sure you know how to find an area of a regular polygon, because if you don't practice this a little more, it'll disappear really quick. See you guys next time.